Okay, welcome everyone to the first virtual day of the conference. Let me introduce the chair of today's session, Shamgar Gurevich from the University of Wisconsin-Madison. Shamgar, please take over.
You want me to introduce now? Okay, maybe I just say to Joseph, happy birthday, and probably for many of us, so for me, Joseph, and it's not just Joseph, Joseph and Tamara are my family, so they really keep in touch with them all over the years, and thank you for this. This is really exceptional and very nice of you, so thank you. So I introduce Roma. We'll talk about quasi-classical approximation to category O and positive characteristics.
Okay, thank you very much. And yeah, it's an honor and pleasure to celebrate another Joseph birthdays and invitation. I couldn't be there in person. Okay, so let me start. I'll start with some history. So in the subject begins from the Joseph's paper from 1976 with Sergey and Israel Gelfand, where they defined category OR, and I think most people know what it is, so I don't write out definition in great detail. So it's some category of modules of a complex semi-simple Lie algebra, where irreducibles can be characterized as modules with the highest weight. So we fixed a Borel subalgebra, and then there's a generator on which is killed by the triangle apart and scaled by the torus. And then there was this other thing developments. Now, very soon after this, there's the heuristic conjecture, the characters of irreducible modules in terms of Kasdan-heuristic polynomials. And it was proved by Joseph Bernstein and also independently by Broninsky-Kashiwara or localization theorem, which will be central for my story. But I also want to mention one later development, also, yes, to a large extent inspired by Joseph's ideas, but and also ideas of Sasha Beilinson and Victor Ginsburg. But the paper was, so it was contribution by Wolfgang Zorgel, who in 1990 proposed a description of category OR in terms of Zorgel. So depending on the version, it can be modules or bimodules. So this is now a very standard and powerful method, and which again I will not talk about in detail, but I can just say whether the Zorgel, whether either module or bimodule, is nothing but a module of a polynomial ring, So we have two copies of polynomial and cartan acting there, and the invariant polynomials should act diagonally. Rephrase it as coherent shapes on this variety. Variety is just a union of all graphs, and this is a wild group acting in this cartan. Okay, so this was a little bit of history. And let me pass to what I want to talk about today. So, okay, just to be more concrete, we can see the category O, it comes in different flavors. And I want to focus for now on a so-called big category OR, so I fix an integral. So yes, I fix this integral regular character lambda, and then I consider this O lambda hat. So this means that the corresponding ideal in the center, externipotently. And from definition of category Y is that the upper triangular part, the radical of Borel, acts locally nilpotently. So this is U is the, I didn't write it, but of course I mean that B equal to T plus U is a Borel. Okay, and so now, as I mentioned on the previous slide, the central result here is a localization theorem from Beilinson-Bernstein, and it identifies our category on lambda with a category of D modules. So because of the specific conditions I imposed, this will be a monodromic D module. So usually people talk about D modules on G mod B. It's what I'm saying here is not very far. It's slightly different. So it's again, of course, in parallel with this decomposition for Lie algebra, I have the Borel subgroup. And so this is Borel, and it's maximal torus and a maximal unipotent subgroup. And so I consider now D modules, which are, well, you can say U equivariant D modules on G mod U. And for the Cartan action, there what's called weakly equivariant with unipotent monodromy. So this is what this MON stands for, monodromy. So irreducible modules are the same so they, as for the G mod B version. So they pulled back from G mod B, but I allow this extensions with non-trivial unipotent monodromy. Again, this is not a super central point, just a particular version I want to use. Yeah, and you know, using the magic formula that G mod H is G mod H square mod G, we can rewrite it as T times T monodromic D modules on the square of G mod U, the base affine space, and things like equivariant under G, and then monodromic for T.
Can I ask what are monodromic D modules?
Yes, yes. Monodromic means weakly equivariant. So the first approximation, they are constant on the orbits, locally constant on the orbits, but the technical definition is that in the when you consider equivariant modules, and it means that say under torus, and the torus acts on the sections, and you require that the derivative of the section equals the action coming from D module, from the D module structure. And here you don't require it. It's so torus still
Another action.
sections, but there may be this little difference between. So an example, like if you just say x equal to t, and then if you take a non-trivial local system, for me on the unipotent local system and local system.
So the always so in what you're doing, so you want the modules to be actually U times U equivariant, but only weakly T,
Yes.
T times T.
Yes, yes. Okay, is this clear? Okay, thanks for the question, and yeah, sure, don't hesitate to have questions. Okay, so now I come to like central point that, well, what are D modules? I again probably don't need to recall the definition in this audience, but well, the modules for differential operators, and differential operators is a quantization of the functions on cotangent bundle. This is the maybe first thing we learn about this concept. And, many of you also learned it from Joseph's notes. Yeah, so I'm just summarizing it here with those weakly arrows. So we have just something very general. So we have some smooth variety X, or for us to be stacked. Thinking about variety is good enough for now. And then there is a classical object, cotangent bundle, and you can see modules of functions from the cotangent bundle, which is, in other words, quasi-coherent sheaf. Or we can have modules of its quantization, which is a D-mod. So again, so we have this classical object, and this is the quantum object. And they connect. So there is bigly arrows don't have much of mathematical content, but just passing from one to the other, from classical to quantum is quantization, and going in the other direction is the classical. Just words to summarize the situation. So let's just see what this cotangent thing is in our case. So the thing is a little bit sticky, but it's still not too bad. So the rule is that, well, this is starting with an actual variety, G mod U, and then we take some G mod U square, and then we take some impose some equivariance condition and some monodramistic condition. So the rule of is that when we impose equivariance condition, we have to do Hamiltonian reduction to the cotangent bundle. When we impose a monodramistic condition, we don't do Hamiltonian reduction, just quotient by T. Just it should be very natural given what I just told, what I just said, answering Rami's question, right? That the torus acts, but we don't impose this equation. I mean, the derivative is free to be what it wants, and so accordingly, we don't on the classical limit, we don't impose the moment equation, but we still quotient.
So you quotient the cotangent bundle by T without taking the fiber of the moment map?
Exactly. But for G, it's almost equivariance, right? To take the quotient. So we arrive at this. If I take this T star G mod U mod T, I get this variety G tilde, which is some people call Grothendieck simultaneous resolution or alteration. In any case, it's something very concrete. You can think of it as, I'm thinking about G mod B as parameterizing Borels. And then it just pairs consisting of a Borel and an element in that Borel. For SLN, it would be a flag, complete flag, and a matrix preserving this flag. Okay, something very concrete, and then we so just specializing this general diagram to our case, we arrive at this thing. So this is our category or, and this is, well, some people call it Steinberg variety, but anyway, so this is like this fiber product of G tilde times G tilde over G. So you have a matrix, maybe I should write this, and this is the pair of X, and then there will be two Borels containing it.
We probably missed, what was the motivation for considering the left-hand side?
Left-hand side because it's equivalent to category or by localization.
This is equivalent to... when you take all the central characters together?
If you will, I can go back to this. Oops. Yes, it is here. Yeah. So you see here the localization theorem identifies it.
When you take all the central characters together, yes?
No. Okay. I'm sorry. So it's not evident in the notation, but when I say monodromic, for me, I only consider unipotent. And so if you want to work with other central characters, then I would have to rely.
But if you fix central character, it's not just B times B equivariant models?
No, because I want, again, unipotent rather than zero. Irreducibles are the same, but they allow more extensions. It's not a central point.
So there is no pure central character. The central character kind of acts importantly. The central acts.
Exactly. This is what it says here. Yes.
I see. Sorry, I missed it.
No, it's okay. So I think it really helps too. Okay, so so I don't like this way of oops. I'm sorry. Just a second. Sorry. All right. So oh, actually, it is back. So yeah. So I was here. So now I want to just okay. So we motivated this thing, and now I just want to connect the things that were said so far. So we have this Steinberg variety, but I just want to make this comment that the Zorgas think that, I mean, it's not how he introduced it, but I just want to point out that it sits very naturally in this picture. Namely, this G tilde to G is it's some complicated map, but over the regular locus, say if a matrix is such that its minimal polynomial equals its characteristic polynomial, then the over this open set, this map is like a ramified cover, a Galois ramified cover, a Galois group W, which corresponds to the fact that for a regular matrix, fixing a flag is the same as ordering the eigenvalues. Fixing a flag resolved by the matrix is equivalent to ordering the eigenvalues. And right, and then I also want to recall that there is this famous constant section from, yeah, of course there is a G goes to the joint quotient, just G mod W, but then there is this constant section, which I call kappa. And now, if I take pre-image of this constant section in my variety, in my Steinberg variety of triples G tilde times G tilde over G, then this is exactly T times T over T mod W that appears in Zorgas theory. Okay, so this is just a remark. So now, okay, just going back to our background philosophy. So the quantization classical limit are not functors, and specifically, yeah, it's say quantization is an art, not a science. In any case, so if I'm giving a D module, then to kind of dequantize it, to take its classical limit, or in precise terms, to associate a coherent sheaf on the cotangent bundle to it, I need to choose a good filtration. And then I can take its associated gradient, and this would be my classical limit. However, there is a theory, I mean, there is an, I mean, of course, one can choose arbitrary good filtration, but that is hard, like the result is hard to control, in particular, it doesn't have good functoriality properties. But instead, if we use the Hodge theory, like a Hodge module, actually, it does come with additional data, and in particular with a good filtration, in Hodge filtration. And then, I mean, we can refer to general theorems in the theory to get powerful functoriality properties of this filtration. So this is like a sample point for me. So we kind of take classical limit by Hodge theory. Okay, so at this point, maybe I can say a theorem, like work in progress with Andre, one of my former students, and Dougal Davis in Australia. So, so we have a full embedding, and it's only not just full on the abelian category, but also on X full, also on X. So it's also, let's say, T-exact full embedding of derived categories, which exactly does this dequantization. So, which sense I call it C for classical limit, script C for classical limit. Yeah, I'll have something else called C later. So yeah, so it's yeah, does this classical limit, and on many objects coming with the standard Hodge structure, it will take this object to the associated gradient Hodge filtration. And then, well, at the level of kind of covering the general ideas, I don't know if it's so important, but as a technical application, it is important that this generalizes to GK modules, where K is invariance of the involution. So this comes up in this type of real group representations. For now, we can show it under additional assumption that theta is quasi-split. And if you're not familiar with this, it doesn't matter. So some technical assumption that we hope to remove. And then the point, just making contact with my remark on the previous slide, that under this functor, the Zorgel functor just becomes the restriction to constant slice. So everything becomes very natural. And I should say, well, I put this remark. Yeah, no. So some remarks. So Zorgel in this GK context, which I'm naming in this talk, too much detail, but in this GK context, under the same technical assumption, the Zorgel functor was generalized to this context in my work with Kari Villain. And so another remark is more like question that, in fact, the Zorgel functor can be alternatively described. It's not the focus for me in this talk, but it can be alternatively described as in terms of just micro-localization by taking generic micro-local stock. Well, I should have written stock, not fiber. But this kind of should be related to the grade of Hodge filtration, but I think the actual relation, it's a question maybe in general theory of D modules, but I think the relation is kind of subtle. And okay, some remark that is maybe important for full disclosure, that, well, first of all, you can, this embedding, you can look at what it does on growth groups, and it actually turns out to be just embedding of the group algebra of the wild group into the affine. So this kind of, in the classical limit, you have the affine situation, and the quantum, I think you have finite. And I should say that, in fact, I knew this A for many years in some form, but only in case A, not in case B. I mean, so that's, and it can be proven in a roundabout way based on this equivalence between two categorifications of W affine or H affine, which is a part of my old work with belonging to this local geometric limit story. But yeah, but this is kind of, in this story, there's no dual group, and there you kind of had to go via the dual group and loop space and then come back, which is not a very direct argument. Okay, so now I want to just tell you a little bit about the idea of proof, and this is maybe the only new part because these ideas were around for many years. So the idea, well, as the title suggests, that it goes for a characteristic P, and it's just well, rather straightforward extension of the ligne-illusie idea. So, but to just make context, let me recall that. Again, something very general. If I take a smooth projective variety, it has its de Rham cohomology, which can be tautologically rewritten as X to indicate of D modules from the O trivial vector bundle with a standard connection. And but it also has Hodge cohomology, just a cohomology of forms. And as an exercise, you can prove that it can be rewritten as X to indicate categorification on the cotangent bond from or X to X again. So here X is embedded into T star X by zero section. And of course, the famous Hodge theorem identifies the two. So there's an actual isomorphism. Okay, it turns away, but it's in fact it stays in our minds. So it's yeah, it's so the two are isomorphic. So I'm just want to point out this is a statement of the same nature that, well, if you want to be more general with consider more general varieties, then you still have some statement of this sort, but only on the subcategory generated by constant shape. And then for it was maybe I should have mentioned that it was generalized by Simpson. Yeah, I should say Simpson generalized for a variation of Hodge structure for so yeah, so we want to prove a statement of this sort, and famously in 1997, the first proofs were analytic, but in 1997, the ligne-illusie proved it by a reduction to positive characteristic, and we are just mimicking this argument. Okay, so how do we mimic this argument? So we want to recall that if X is a smooth projective variety, I mean projective actually is not important here. A smooth variety over characteristic zero field, then the sheaf of crystalline differential operators forms an Azumaya algebra of the cotangent bundle. And it never, unless X is.
Here, zero should be positive, right?
Oh, sorry. Yeah, this is a type. Thank you. Thank you. Right. So it's and it never splits. So maybe I should recall that Azumaya algebra. So if A is Azumaya algebra, A splits means that A is Morita equivalent to or. Well, it's equivalent to A is the algebra of endomorphisms of some vector bundle. But this is equivalent to saying that A is equivalent to or in sense of Morita. And it never splits everywhere, but it sometimes splits in some subvarieties. And then if it splits on the support of M, then we can just apply this Morita equivalence to an A module and get an O module, which is quasi-coherent sheaf. And then we call, following Vygotsky, we've called this operation, this functor, which depends on the splitting, but but assuming the splitting is fixed, we can get a functor, and then we call this functor Cartier transform. Okay. And so now I'm about to explain the central statement in this project, so this proposition, which will form the implied theorem. Okay, so I'm saying that for objects in our category, Cartier transform is well defined. I mean, basically, the algebra never splits for a positive dimensional variety, but it can split for a stack. For example, there can be an interesting stack of dimension 0, and then I think, at least in some cases, you can show it splits on such a stack. In any case, so the yeah, I'm just summarizing the situation by saying that the Cartier transform is well defined for objects in our category, where I mean, originally everything was defined over C, but here, of course, everything is now over K, where characteristic of K is P. And so it produces an coherent sheaf on G tilde and G tilde. And yeah, I didn't mention it, but they will all be automatically supported on the pre-image of N. An important call. And then I put this B in red because this is the central one, the most interesting statement. So for generating objects, say for standards, well, they have a natural Hodge lift. This just by functionality of this Hodge modules theory. And then I'm just saying it's essentially Gur M tilde, I quote M tilde this left. And the point is that the coherent sheaf that I get by taking associated gradient agrees with the Cartier transform. So the slogan is that the Hodge gradient is identified with Cartier transform. And so, well, I mean, technically, I mean, these are over different fields. So for this reason, I say agrees rather than isomorphic, but the meaning should be clear. So we usually spreading arguments. So you can either say that you define your D module over some finitely generated ring over V, and then you extend the filtration and can decide with good filtration, which is the Hodge filtration we see, and then you take associated gradient for characteristic P field, and then for almost all P, you recover the same thing as Cartier transform. And yeah, I'm here. It's maybe not so much about the proposition, but for the co-standard object, actually, one can compute both sides very explicitly, and you just get the structure sheaf of some subscheme. Well, maybe if I have time at the end, I'll talk about this a little more. But yeah, this is a very concrete example of what it means they agree, namely they are all equal to the structure sheaf of some subscheme defined over Z and base change to your. And then the last part, okay, is statement of a different nature that but it's not a hard statement that if I take important matches modular G, then it's homologically finite, meaning that X is total X is finite dimensional for any base field for any. Of course, I mean here that FG are coherent. F and G are coherent sheaves on N, G. Okay. Well, maybe I should ask any questions. Explanation of all the social statements. And then I'm going to say that the proposition implies a theorem by Deligne-Éleusis method. So, okay, I didn't explain on the slides what it means, but it's just basically the statement amounts to degeneration of some spectral sequences. For example, if I take standard object and co-standard object, this is graded for both, and then basically I want to check that there are no high X between associated graded. So yeah, the proof reduces to statements of this sort. But the point is that using, say that, using B, we realize some X in the category of coherent sheaves. Both, so on the one hand, it can be X between D modules. So when everything happens over K of characteristic P. But on the other hand, X in coherent sheaves is a on the other hand, over C, you can write a spectral sequence like this deformation spectral sequence where X in coherent sheaves converges to X in the D modules category. But then using, the answer to X between D modules, given the finite nature of the situation, it has to be the same for almost all characteristics. And so it shows that this the dimensions of this X are the same, and so this spectral sequence degenerates. So I didn't put in the slides because this is kind of exactly parallel to the Deligne-Éleusis argument. Okay, any questions here? So yeah, I just want to talk about this proposition B because I think it's well, we use it as a technical trick, but I think it's some very interesting structure on these D modules. And in fact, I just first the proof is kind of in a way not very conceptual. So our say if we want to do it for standard and co-standard objects, we do it for simple reflections where we compute things by hand. And then we use that both sides are compatible with convolution, and so we get some isomorph. So this is what's summarized here.
Roma, can you show us part B again?
Yes, of course.
Thank you.
So I'm just saying that associated graded of Hodge filtration agrees with Cartier transform. Okay?
Can I ask a question? The left-hand side because it's 0, right-hand side because it's P. What do you mean they agree?
Yeah, that's what I was said. That's what I said verbally. That there exists an object over finite localization of Z, which specializes to all this. Okay.
I'm happy. Thank you.
Okay. So yeah, and so yeah, I just want to say that a similar structure does appear in mathematics, but to my knowledge, people were not considering general holonomic D-modules there, but more things like variation of Hodge structure, and then Faltings and then Fontaine. I mean, people working in p-adic or p-Hodge theory, they have this definition. There is something defined over the p-adics, but over if you specialize to characteristic P, you exactly get this structure. So they were considering, yeah, M for them was a bundle with connection and with Hodge structures, or variation of Hodge structures. And so in our terms, like support as this Cartier transform, set theoretic support as a zero section. But in that setting, yeah, they consider these objects, you know, vector bundle with a connection with a good filtration, and then as part of the data is identification of Cartier transform with associated graded. And so this is known in literature as Fontaine-Lafay module. And well, this is the next thing I'm saying here is very speculative, but so tempting, I think. So I just want to point out that Kazan-Lustig conjectures, well, basically, Joseph's argument with Joseph Bernstein, it reduces it to some things in algebraic geometry, and well, they use Frobenius weights, but one can also use Hodge weights. And so basically, this Kazan-Lustig conjectures and many generalizations, including something I did with Merkovich, which has to do with G modules and characteristic P. These are all proved eventually by, at least you can phrase it this way, that they all eventually deduced from properties of Hodge modules, weight filtration, C. And it's very tempting to say that this p-adic Hodge theory, of which we here see a very tiny little piece, should play also an important role in representation theory. And well, there's a speculation, you know, you can study Janssen filtrations, and again, there's this famous work of Joseph with Sasha Bernstein on Janssen conjectures for over C, but Janssen originally introduced them in the context of mod P and story representation theory. It's lived to ZP, so this is an HL kind of ground for applications. But okay, this is very speculative. All right, so well, I can pause for questions, but then I also wanted to talk about applications in further directions. So basically, I explain what I wanted to explain about the theorem and idea of proof. So, other questions? Okay, so I can proceed. Okay, so first, like motivating application, it's this causal duality for GK modules. This is Jovic conjecture. Again, this is done for quasi-split theta in my paper with Milonin that I already mentioned. Kind of using the same ideas and using this version of Jovic funct that I mentioned, that we can now interpret as restriction to constant real slice. But yeah, the hope is to, I mean, we've been working for many years with Kari on, and now with Zhiwei Yun and Andreona from the general case. And I think we have good ideas, but this would be this theory should give another approach. But I just want to mention some feature that I feel is quite interesting. I mean, again, I don't want to explain the theorem, but just the key feature is that this functor S, the orderly functor, which we interpreted as restriction to constant slice, but then there is this causal dual picture, there is some causal duality, and then on the dual side, it just becomes equivariant cohomology. And so, yeah, I think there are similar phenomena observed in geometric Lagrange, maybe even some before. I thought about it, and well, I can be more precise that maybe I didn't write it, but so there is this derives geometric Hecke. Well, I did not talk about loop groups so far, but I think this is okay. Everybody in this audience likes them. So, and then so this is, well, again, this is kind of, maybe I should better say this is causal dual. To coherent sheaves on the Lagrange dual algebra, equivariant under conjugations. And so this is, well, was written in our paper with Misha Finkelberg, but it's essentially goes back to ideas of Victor Ginsburg and Drinfeld. And it has a similar feature that here we can take restriction to constant slice, and here we have equivariant cohomology. So it seems to be like a general phenomenon, which I think good to understand better. Okay, so this is one thing, and another point. So it also involves loop groups, but in a very different way. Now I just replace G mod B. So well, I stated here in very general terms, but I just say it here that well, we replace G by the loop group, replace B by Iwahori, and well, U by theoretical. So G mod B is replaced by the affine flag manifold. And so you can still consider equivariant D modules or monotromic D modules. That's all well defined. All these things have precise analog. And we conjecture, well, I conjecture that again we should have a full embedding from the category of D modules to the category of coherent sheaves on the cotangent stack. But now coherent sheaves on this cotangent stack is actually a categorification of Daha, double affine Hecke algebra. So this is yeah, this is mentioned here. So, well, there's double affine Hecke algebra and categorification of double affine categorification of double affine Hecke algebra. And there is a conjecture that the Hecke categorification for G and G check are naturally equivalent. And so this is related to classical limit of geometric lengths. And so here I'm saying that, you know, if I have this full embedding from D modules to coherent shapes, then by as I put some time ago, I mean this category of D modules right here, that D modules on well, flag not I, symmetric. So this is equivalent to the category of coherent shapes on, well, for the dual group. And so of T star. I'm just passing from monodromic to equivariant version to simplify notation, doesn't really matter. But the point is that this, it's kind of this cotangent thing for finite dimensional group, but this sits inside, like your original group sits inside the loop. And so this thing sits inside T star of LG check. So this functor coming from Hodge graded should be swapped with this functor coming from embedding of constant loops. And this, I mean, may give a way to approach this conjecture. Okay, and well, finally, maybe I want to mention generalization in another direction. So for symplectic resolutions, yeah, again, playing with this monodromic versus equivariant version, you can rewrite, like you can write a version of theorem A, where we'll have just D modules on G mod B, which are U equivariant, and this is going to be embedded into B equivariant coherent shapes on G star G mod B, but Borel under the moment map. And so one expects that one can replace this B here by T, and one still gets it for embedding. So the start of this conjecture is that I remember discussing it with Sasha. A few years ago, I had discussion with Sasha Berman, who said that physicists like Gayota expect something like this. And I remember saying then that I can prove it, so I couldn't reconstruct it as I was preparing the talk, but maybe, hopefully I will at some point. But in any case, if the reason I want to change B to T is because then it can be has a direct analog for other symplectic resolutions, and I hope it also generalizes there. Okay, so maybe it's a good point to stop. And of course, last but not least, I want to wish Joseph a good birthday and thank again for all the wonderful mathematics he created and taught us, and for many other things. Okay, so that's here. So any questions?
Can you give some references where I can look at this?
Yes, yeah, sure. So, okay, to what? So well, the main theorem is unfortunately not written yet, but I can certainly send it to you and it will be written. But let's see what's the most Yeah, maybe that's the best thing I can say. But
just is there some relation with this AUZ proof and
yeah. So
some explicit.
no, for this.
So
I think, I mean, well, there are references in this literature on pedic course theory, which I am myself not really well versed, but I can look for references and maybe send it to you. What for me, like at least some of this is maybe in this August Volodlowski, where they develop
okay,
part of this picture, but yeah. But yeah, I'll wait. I'll try to send yeah, so maybe sorry, I forgot to make this comment. So said I want to return to this point about associated graded of the cotangent module. Okay, so first maybe if I have it, I can give a more precise statement. So and then yeah, there's some twist of my horn. So ZW is the following. You just take let's just take this thing as we said we considered before, and then it contains G tilde times G tilde over G, and we like red. So we take the pre-image of the regular locus. And on G tilde reg, we have an action of the Weil group. And so this contains just a graph of the action of W. And then the ZW is the following, and just take the closure of the graph when I intersect G tilde with the pre-image of N. No, let's try it inwards. In a way, I like this formulation because, you know, in general Springer theory, they say, you know, they motivate the Springer theory by saying that we have this action of W generically, and then you somehow degenerate it, and then there are different techniques to degenerate it. First an extension, something else. And so this is a statement of this sort. But I should say that yes, our theorem. So I was focusing on unipotent monodromy. You know, Rami suggested I should consider other monodromies, and I agree. And so this should generalize. And I think our method just works to rational, non-trivial to rational, but non-integral lambda.
Yes.
In this case, I mean, so this is again this is the description of associated graded for Hodge filtrations. You know, in many cases it's not easy to describe, and I think this description, and it has many applications. So now there's this program of Villain with Schmidt, which was realized partly in his collaboration with Dougal Davis, where they applied to study unitary modules or like unitary GK modules. And I'm just I just hope that this should give more information about the. I mean, there's no such easy formula in general, but maybe so hope is that it should give. Allows would allow to compute replies to computing in some sense. Okay. Well, then it will be not for them. It's a local system. Okay, so this is just. Okay, any other questions? Okay, thank you. So
Okay, let's thank Roma again.
virtually.
Dima, we have now like 15 minutes break.
Yes.
Okay, so people are welcome to chat here. Dima, you want to mention something for tomorrow? What's going on tomorrow?
Yes, so tomorrow we meet at the same time as today, which is 4 Israeli time, like 1 hour ago, from time like now. And also tomorrow there will be no recordings. The lectures didn't want to be recorded. So come, please come. They will not be repeated.
Actually, Dima, can I share screen meanwhile?
Sure.
Okay.
So we have
So you
13 minutes of break left.
okay, so you hit in 30 minutes, yes?
Yes. Yes.
So Dima,
Yes.
so you see it now, so it's now okay, yes?
Yes, we see it.
Yes.
Okay.
It's a little bit
It's blur.
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 Well, I'm not sure I can do anything about this.
Try to write on it.
Just a second.
Yeah, it's a little bit blurred.
Can you take a more dark black?
This is the most dark black.
Okay, it's not that bad, actually.
That's strange. It's,
Well,
Maybe close and open, like they do in computer science.
Yes, maybe.
what?
try to
Close
do
and
it.
open it again.
Open whom?
This shared screen or something.
Stop share and begin share anew.
Well, okay.
Nah. Okay.
Well, this I don't actually know.
Okay.
So I see it on my screen. Okay, so no?
It's quite good anyway.
Hmm?
Not that- It's quite good anyway. It's not that bad.
Not that bad. Okay.
It is a bit blur, but it's not.
So does it help if I write like, okay, so let me try experiment a little bit with this.
This is difficult to read.